Log on, tune in, find out. Another good idea from Cambridge.
Does it work? No. It's on. This should be on.
Okay.
Is okay?
Okay.
Okay, so first of all, before starting, I'm very glad to be here in Cambridge for this conference, and I'm extremely grateful to the scientific committee for inviting me here. So actually, the work I'm going to present started in the 2007. So at that time, one of my co-workers, Ralph, was here for the Newton period on high oscillatory problems, and we started this project about that time. And the results I'm going to present this morning have been obtained in collaboration with Ralph Hitzmaier and with Andrea Moiola, who's now PhD students at the ETH together with Ralph. So I will, before giving the outline of my presentation, I will start just to warm up with the first model problem I'll be considering in this talk, namely the Helmholtz equation. So we consider time harmonic wave propagation, and for simplicity we consider homogeneous media. And we start with a domain, which is a polygonal or polyhedral domain, depending on the space dimension. Omega is the wave number, which is proportional to the reciprocal of the wavelength. And I'm considering a boundary, an inhomogeneous boundary datum, G. And I write here the Helmholtz equation with the constant coefficient. Here I assume for a moment to have a general right-hand side here, but then I will consider the homogeneous case of f equals to 0. And I supply the problem with the impedance boundary condition on the boundary domain. So this problem is hard to tackle from a numerical point of view. So in my presentation, I will concentrate on finite element methods. So I'm not talking about boundary element method or other type of methods. And I will focus on the finite element approximation. So I come from the finite element world. And together with Ralph, we wanted to try to study finite element approximations of this problem. So all the people working on Maxwell equation, on Helmholtz equation, know that Helmholtz equation, especially for in the medium and high frequency case, are difficult to be approximated by finite elements. So let's consider the simplest possible problem, test case, 1D numerical experiment. So this is the homogeneous Helmholtz equation in an interval, and assume to have a Dirichlet boundary condition on one side and impedance boundary condition on the other side. In this case, the analytical solution is just a plane wave in one dimension. And I consider the wavelength to be 0.16. So the domain is 0,1. So assume that you want to approximate with linear finite elements, which is the simplest possible finite element discretization you can think of. So if you take several elements per wavelength, namely 8 elements per wavelength, so what you see is that the phase error is tremendous. In fact, so the number of elements per wavelength to be fixed in order to avoid this phenomenon is about 10. But it's a lot, especially because you are trying to approximate a very easy problem. So the reason behind this can be the so-called pollution effect. So the numerical evidence shows this. So if you approximate the Helmholtz problem with piecewise linear functions, so the Galerkin error is of the order of omega h squared times omega. Whereas if you compute the best approximation error, which means that you want to see the best possible P1 elements closer to the analytical solution of the problem, the plane wave, so you see that the best approximation error is of the order of omega h squared without the omega in front of. So the ratio between the Galerkin error and the best approximation error increases with omega, and this is a source of troubles. So the idea that several people had were to try to insert the features of the problems, namely the frequency, but let's say the information from the whole equation within test and trial spaces. So instead of using simple polynomial spaces, people started using the so-called Trefts finite element methods. So the idea is that you take trial and test functions which are solutions to the homogeneous equation you want to approximate. In such a way, you transfer some information from the equation within the approximation spaces. So I take here, so assume that you have a mesh that I call tau h, th, and this is this capital T of the mesh means Trefts space on the mesh th. So I take my discretization space as piecewise H2 functions, which are element by element solutions to the homogeneous, in this case, Helmholtz equation. In this way, one can hope to approximate a solution of the Helmholtz problem in a cheaper way, because somehow these test and trial functions contain information from the equation. And secondly, so you want to go to a P version of the finite element method. Why? Because H version versus P version. So H version of the finite element method means that you are keeping refining the mesh to improve accuracy. P version of the method means that you choose a mesh which is appropriate for your problem, and then instead of refining the mesh to improve accuracy, you increase the dimension of the local spaces in such a way that you improve the approximation by enriching the local spaces. I mean, element by element, you increase the number of degrees of freedom. So the elements are fixed, and you increase the number of degrees of freedom within each element. And the idea to use a P version is because the P version is immune to pollution effect, which means that so basically when you approximate the Helmholtz problem with an H strategy, with an H finite element method, what you see is that for a while you basically refine the mesh and you don't improve the approximation. At some point you start improving the approximation. So the idea is you choose a mesh fine enough to approximate in a reasonable way the problem, and then you increase P. So you fix a quite coarse mesh but fine enough, and then you increase P. So the idea of what we started to study was to use the Trefts finite element methods in order to be closer to the equation within each element, and then to use a P-version strategy to avoid the pollution effect. So, but then, I mean, the question is obvious. What are Trefts spaces for instance, in this case, for the Helmholtz equation? So for the Helmholtz equation, examples of Trefts basis functions within each element are, for instance, plane waves, which are solution to the homogeneous Helmholtz equation. And here I basically listed some of the methods that you can find in literature using this type of strategy. I mean, instead of polynomial finite elements, you can use plane waves linear combination of plane waves within each element. So in this case, the plane waves have the same frequency as the problem, and then you can choose as many directions as you want within each element. So in this case, the P version of a plane wave method will be to increase the number of directions within each element. So I will mention some of the methods that you can find in literature. The partition of unit methods using plane wave as approximation spaces. So in this case, you have plane waves multiplied by a partition of unit, and you end up with a conforming method. The ultra-weak variational formulation by Cesena and Deprez, they use a plane wave only, and they use I wrote exotic formulation of the method. So basically, they remove all the internal degrees of freedom and they solve the problem on the mesh skeleton only. Then the plane wave least square methods by Monk and Wong. So in this case, they approximate the transmission and boundary conditions by writing a least square functional on the mesh skeleton. The discontinuous enrichment method by Farhat and the co-workers, they use plane waves and they impose the continuity constraints by using Lagrange multipliers. The variational theory of complex rays, so they use plane waves and the amplitude depends on the wave vector, which means the directions time the frequency. And then a class that we call the plane wave discontinuous Galerkin methods, which is like a generalization of the ultra-weak variational formulations. But I mean, plane waves are not the only possibility to write down Trefft's methods for the Helmholtz equation. Another possibility are the so-called Fourier-Bessel functions, which in the literature are also known as generalized harmonic polynomials. Then I will explain later what a generalized harmonic polynomial means. And so you can find here in this class of methods the same strategy of methods with plane waves, but just with different basis functions. So for instance, again, the partition of unit methods with Bessel functions, least square methods by Stoyak, Monk and Wong, Barnett and Betke, and the ultra-weak variational formulations with Bessel functions. So basically the problem, when you pick your favorite Trefft's space, then you have a problem how to impose continuity conditions across interelement boundaries. So if you use polynomials, you pick the degrees of freedom on the interelement interface, on the interfaces between elements, and you enforce the matching. If you want to have a continuity, you impose that the traces from one element and the one from the other side do coincide at the interface. But now in this case, that the degrees of freedom are something which are strange with respect to the usual polynomial ones, you have the problem of imposing the continuity across interelement boundaries. So one possibility is to use the partition of unit method. So basically you multiply by a partition of unit system of functions and you end up with a conforming method. So your approximating functions are continuous. Otherwise, you can relax the continuity constraint. So the continuity constraint can be relaxed by imposing it with the least square methods, or by Lagrange multiplier, or in a discontinuous Galerkin fashion. So what I'm going to present here is actually Trefft's method with a within a discontinuous Galerkin framework. So I will explain, so since basically everyone knows what a least square method is, or Lagrange imposition of constraints by Lagrange multipliers is. So I will focus on this one because this is what we study in deeper. So then, of course, everybody can have a question. So since you have to use a P method if you want to avoid pollution, why one should use Trefft's instead of polynomials? So basically, if you only care about theoretical properties and not about computational cost, that's actually the same. I mean, if you take the P version of a finite element method, so this is pollution-free like a Trefft's method. But then, so what you see from the dimension of the spaces and their approximation properties and from numerical results, that if you use Trefft's, compared to polynomial methods, you can have the same accuracy with less degrees of freedom, which means with larger elements and less degrees of freedom per element. And so if you care about computational cost, it might pay off to use these functions which are better adapted to the problem you are considering than general polynomial functions. So basically, in my presentation, I will concentrate on Treft's discontinuous Galerkin method, which are general discontinuous Galerkin methods with the Treft's basis functions. And the outline will be the following. So I will start with the derivation of the Treft's discontinuous Galerkin finite element methods for the Helmholtz equation. I will present the p-version analysis of this method. Then I will probably give some hints on the best approximation estimates of Helmholtz solution by Treft's functions. And then I will show something about Maxwell's equation, which are the second model problem that I will be considering in my talk. So I will start explaining everything on Helmholtz, which is easier. So then when everybody knows everything about Helmholtz, I will point out something on Maxwell, which is more complicated. So let's see about the Treft's DG discretization of the Helmholtz equation. So the first part is just discontinuous Galerkin discretization. In the end, we will choose Treft's basis functions. So in order to write down a discontinuous Galerkin method, what I do, so I will start, this is the equation basically. So I will start by introducing a new variable sigma, which is such that I omega sigma is equal to the gradient of u. And then I will rewrite this equation in terms of sigma. So I will leave this term unchanged. And here I write minus divergence of gradient of u. By gradient of u is this. And then I also translate the boundary conditions in terms of sigma. Now, usually when you write a finite element method, you take the equation, you take the variational formulation, then you take your mesh. When you do discontinuous Galerkin, you do the other way around. So the first thing you do before writing the variational formulation is that you introduce the mesh. So you introduce your mesh with possible hanginess. I mean, it can be an irregular mesh. And then you write the variational formulation of this mixed problem, so this two-variable problem. So you just multiply by test function and you integrate by parts, element by element. So you don't write the variational formulation on the whole omega, but you write the variational formulation element by element. This is again on the continuous spaces. Now you want to discretize, so assume that you have discrete spaces for the vector valued variables and for the scalar valued variable. And then here, instead of sigma, tau, u, and v, you take sigma, the discretization of sigma, of t, of u, and sigma, tau, u, and v. So you basically pick. So I write the sub-index h and p because h, to remember that we are on the mesh, on a mesh with the size h, and the p, to remember that in each element I have a p degrees of freedom. So I take discrete spaces, I take discrete functions, and here this is just what I wrote before, just putting hp as a sub-indices. But then I did also something different. Here I put some hats, which means that I will choose discrete spaces, but then on the inter-element boundaries, I have to choose the so-called discrete numerical fluxes. I mean, it's not just enough to write discrete traces, because then for these traces, for these numerical fluxes, these have to take care of imposing the continuity at the inter-element boundaries. So it's not just enough to take here the trace of my function u within the element k, but I also have this term also has to make in communication the element k with its neighbor. So this u hat and the sigma hat can not only depend on the degrees of freedom within the element k, but also have to take care of the degrees of freedom coming from the neighboring elements. And so we have to choose the discrete spaces and the expression of the numerical fluxes. And we want that the gradient, the piecewise gradients of the scalar functions are contained in the space of the vector valued function. Why? Because I want to choose here tau as the gradient of v in such a way that if I can choose tau as the gradient of v, you see that this term becomes equal to this one. So I can take this one and replace in the second equation. And then if I'm careful enough to choose a sigma independent, I mean only depending on u, on the scalar variable, then I end up with an equation in one variable only. So basically, I introduce an auxiliary variable and then I eliminate it. So I end up with this formulation. I integrated by parts once more, but believe me, this is the formulation. And then, so if you want to do standard discontinuous Galerkin, you are done. This is your formulation, standard discontinuous Galerkin formulation. Now you have to pick the discretization space and the definition of the fluxes. But now we are going to use a Trefts, not standard DG, not polynomial DG, but Trefts DG. So I'm going to take discretization spaces where the functions within each element are solution to the Helmholtz equation. So what we are going to do is that we integrate by parts once more this in such a way that all the derivatives go to the test functions. And if I compute everything, I see that here I have this one with the derivative here and this one. I have the Helmholtz operator on the test function. So if I take a Trefts space also as test functions, so this term is 0. And I end up with a formulation which only lives on the inter-element boundaries. So I basically eliminate all the internal degrees of freedom. And this is the setting of the ultra-weak formulation by Cesena and Deprez. So the ultra-weak formulation of Cesena and Deprez can be seen as a discontinuous Galerkin method with Trefts basis functions. And so this is my formulation, it's just this formulation without this one. So I don't want to spend much time on the choice of the numerical fluxes, but for people who are familiar with this continuous Galerkin method, this is one of the possible choice of the numerical fluxes. So basically, this term here and this term here are the averages, average of the gradient, average of the function, which are there to have a consistency of the method. And here, these are jumps of the scalar function and jump of the gradient, which are here to give stability to the method. And this and this are parameters that can be chosen. So the ultra-weak variational formulation by Cesena and Deprez can be obtained, as I showed, just by putting these parameters equal to 1/2. And this was observed in several papers. But then, I mean, you're not forced to take a constant flux parameter. So you can also take flux parameters depending on omega, on h, and on p. And in this way, you can, let's say, you can stabilize in a better way the method. So you have a freedom, basically, to choose parameters, either constant or mesh p and frequency-depending parameters. So this is the scheme of the analysis I'm going to present. So I partitioned the analysis in 3 steps. So the first one, and so in 3 steps, I indicated here ingredients and here results. So the first step, you choose a suitable norm, which is not a norm in general for general functions, but which is a norm for Trefts functions. So remember that a Trefts function have some local properties. They satisfy the homogeneous equation element by element. So we choose a suitable mesh skeleton norm in such a way that you can write your formulation, your discrete variational formulation, in such a way that the bilinear form is coercive and continuous in this norm. And so you have for free well-posedness of your discrete formulation and the quasi-optimality in this strange norm. So basically you know that you are almost safe because your problem is well-posed and you have quasi-optimal error estimates in this strange norm. But then maybe you are not satisfied with this strange norm. So you would like to have error estimates also in a more standard norm, like in the L2 norm, for instance. And this comes step 2. So step 2, ingredient, you use the elliptic regularity of your continuous problem and the stability estimates. Here you want to use a duality argument, so you write the adjoint problem, continuous problem, and you exploit elliptic regularity and stability estimates for your inhomogeneous adjoint problem, and then with a modified duality argument, I will go into details soon, you end up with L2 norm estimates. So, but basically these estimates are what I call abstract error estimates, which are written like quasi-optimal error estimates, which means that the norm of u minus your approximated solution is smaller or equal than some coefficients depending on something, times the best approximation in the approximation space. But then you don't have the order of convergence. To have the order of convergence, you have to find the order of convergence of the best approximation estimates. And this comes step 3. So if you find the best approximation estimates, which means, so you take your solution and you have to find a discrete solution which is as close as possible to your continuous solution, so the best approximation in your approximating space. So if you're able to find the convergence orders of this best approximation space, then you have convergence orders for your method, for the approximation, your Galerkin solution. And so basically in step 3, you can find convergence rates. So Andrea Moiola's presentation will be basically about step 3. So I will jump on it, or I will just give some hints about that if I have time, but otherwise, and his conference will be on Wednesday, right? On Wednesday. So basically the results he's going to present are the one that allows to translate this abstract error analysis into convergence rates, depending on basically we are mainly interested in P convergence rates, but the results are HP convergence rates. So don't look at this. I put this one in gray because otherwise this slide is too. So let's see how to choose this strange norm, because now I start with the step 1. I want to choose a suitable norm in such a way I have my theoretical properties needed in order to have well-posedness and quasi-optimality of my method. So now we want to choose this norm in a clever way. So how do we do? So first of all, so since I wrote this method in this way, in the u variable only, because also sigma, you see, only depends on u. So then I can write my method in an abstract way, in this way. Bilinear form of u, find u such that for all v, a of u v is equal to L of v. So basically I wrote everything in the most standard way. The method is consistent by construction, because I choose the numerical fluxes in such a way that the analytical solution do satisfy my numerical method. So the method is consistent by construction. And now I want to choose a norm in such a way that this bilinear form is continuous and cursive. And this is what I'm going to do. So if you write this norm, I don't want you to read all the terms, but they need to be there just to show you what the imaginary part of AH of UU or WW is. So this is the expression of my bilinear form once I have substituted the numerical fluxes. Now, so for general functions, I leave this like that. But now I remember that I'm working with Treft's basis functions. So every time I integrate by parts and I find something with the Helmholtz operator within one integral, I can remove it because I have Treft's basis functions. So I use this, I do integration by parts element by element, and I found that if I take test and trial function to be coincident and to be Treft's functions, so the imaginary part of my bilinear form, only this part gives contribution to the imaginary part of the bilinear form computed with the same arguments. So basically, the imaginary part of A of WW, it's something that only contains jumps of the function and of the gradients of the function across interelement boundaries. So these are the collection of the internal sides and traces on the boundary. So basically, I found that the imaginary part only contains terms living on the mesh skeleton. I can find immediately that this one defines a semi-norm, but actually, if I'm on Treft's functions, this is a norm, which means that if this one is 0, if all the jumps of functions and of gradients are 0, then my Treft's function is 0. This is not true for a general function, because if you have a function with 0 jumps and 0 jumps of the gradient, of course you don't have 0. But if you do have a Treft's function, this is 0. So this actually defines a norm on the Treft's function. And since my analytical solution is Treft's, because it satisfies homogeneous Helmholtz equation everywhere, and my discretization space are Treft's functions by definition, then also the error is Treft's function. So everything is fine if I measure the error in this strange norm. And in fact, so this is a norm. I need to add some averages just to have a continuity, but the important thing is that, so I have coercivity by definition, and I can prove this continuity. And the good news is that, so even if I cannot just put this norm, but I have to augment it with some terms, but this term have the same, I mean, this richer norm has the same best approximation properties as this norm. So this is just a technical, it's not a problem, and doesn't going to spoil my convergence rates. So this is perfectly fine. So I have continuity and coercivity. So for free, since the method is consistent, the bilinear form is continuous and coercive, then I have existence and uniqueness of discrete solutions and quasi-optimal error estimates. So the error is controlled by a constant times the infimum between the analytical solution and any function living in the discrete space. Now we have an error bound in this strange norm, and we would like to have an error bound in the L2 norm. Usually, when you do that by finite elements, you apply a duality technique, but here that's not possible. So first of all, you assume the domain is convex because you need elliptic regularity of the continuous problem, and then you have to assume that the mesh is shape regular and quasi-uniform. The problem is that the standard duality argument doesn't work for a p-version analysis of the Treft's problem, of a Treft's method. Why? Because if you do the standard duality argument, you have to consider the adjoint problem. Here, you cannot remember, but I switched the sign here. So my original problem is a plus sign here. So then, since it's a second order operator, the adjoint equation is the same, and I only have to change the boundary condition. So usual duality argument, you want to put here the error, and here you take the homogeneous boundary condition. But then the error usually, of course, is different from 0. So you have to analyze the adjoint problem with non-zero right-hand side. But then when you want to apply your duality argument, you want to approximate this dual solution. And since your discretization space is a Treft space, but then you cannot expect to approximate this solution of an inhomogeneous equation by a Treft space, because the Treft space have good approximation properties if the functions to be approximated satisfy the homogeneous Helmholtz equation. But otherwise, you also have to take into account these low frequency terms coming from the fact that the right-hand side is no longer 0. So basically, you cannot expect to have a high order approximation in P of V, which is a solution of a inhomogeneous Helmholtz problem. So basically, you don't have a convergence in P of your best approximation. So you resort to a modified duality argument that was basically in a paper by Monk and Wong. So you write, because what you want to do, now you have an error estimate in this norm and you want to bound the L2 norm. So if you can bound the L2 norm by this norm, then you are all set. So what you do is basically you write the L2 norm as the supremum of when phi is in L2 of W phi divided by the norm of phi. Then you consider the adjoint problem with right-hand side phi, any L2 function. So you replace, instead of phi, you replace this. Then you integrate by parts, you use the Trefts property of your functions W, you use trace inequalities, and the most important, you use stability estimates of the inhomogeneous Helmholtz problem, and you basically derive a bound of the L2 norm of any Trefts function by constant depending on omega and on h times your skeleton norm. So basically, once you have, since we already have estimates of this, then we automatically have estimates of the L2 norm. So the crucial thing are basically stability estimates of the inhomogeneous problem. Basically, you have that the H1 norm is stable with a constant independent on the frequency, and then the H2 semi-norm is bounded by the datum with a constant. This one is independent of omega, and this one depends on omega in this way. So then you put together and you have this bound, and you end up with L2 norm error estimates. So you take this bound, which is true for any Trefts function. Since the error is a Trefts function, then you translate this one for the error, and that's it. So this is basically the analysis. So this is a summary. So skeleton norm, well-posedness, and quasi-optimality in this mesh skeleton norm, elliptic regularity and stability estimates for the inhomogeneous adjoint problem. You derive L2 norm estimates by a modified duality argument. And then step 3, so we are not done because I just performed what I called as before an abstract error analysis. Now we would like to, so since you have here this one, to have an error analysis you need to make this one explicit. So you want to find convergence rates of this. So if you're interested in the H version analysis only, you can do something better by choosing the flux parameters depending on omega, h, and p. So everything I said here are basically either for the constant flux parameters or for the HP omega flux parameters. But if you only want to concentrate on the H analysis, you can do something a little bit better. So these estimates are not, in the end, when you derive quasi-optimal error estimates in H, they are not optimal actually. So you lose something. But with a different, with a better choice of flux parameters, you can recover everything you have for any standard discontinuous Galerkin method. But I mean, I don't want to waste too much time on the H version analysis because I don't want to concentrate on that. So now we are here. This is the missing part to have error estimates. I just want to refer to Andrea's talk and just to say one thing, which is the main ingredient to derive this best approximation estimates. So first of all, we can bound the best approximation estimates in this mesh skeleton norm by best approximation estimates in standard weighted Sobolev norms, and then we want to study error estimates in Sobolev norms. So you pick your favorite Trefts discrete space and you derive a best approximation estimates in weighted Sobolev norms using Vépois theory. So Vépois theory is basically based on Vépois operators. So there exist two integral operators, V1 and V2, which are continuous and inverse to each other, that map harmonic functions into Helmholtz solutions. So you take a harmonic function, you apply V1, you have an Helmholtz solution. You take this Helmholtz solution, you apply V2, and you get back your harmonic function you started with. So basically, you can have from approximation estimates of harmonic functions by harmonic polynomials using the continuity of these operators. So you translate these approximation estimates into approximation estimates of a homogeneous Helmholtz solution by the so-called generalized harmonic polynomials. So generalized harmonic polynomials are nothing but you take harmonic polynomials and you apply V1. So this is the definition of generalized harmonic polynomials. So harmonic polynomials satisfy the Laplace equation. Generalized harmonic polynomials satisfy the Helmholtz equation. So this is basically the setting of this Wequas theory. Then, if you are able to write down approximation estimates of generalized polynomials by your favorite Trefts functions, just by using triangle inequality, you end up with approximation estimates of homogeneous Helmholtz solutions by your Trefts functions. So if you take as Trefts functions the generalized harmonic polynomials, you stop here. Otherwise, you also have to perform the last step. So this is just generalized harmonic polynomials are circular waves in 2D and spherical waves in 3D. And in 2D, the HP convergence rates are fully determined, whereas in 3D, the H convergence rates are fully determined, while the P convergence rates are determined up to a parameter which depends on the element shapes, unfortunately in an unknown way. So this is the only gap in the theory we developed. So this is just the example as stress function plane waves, but Andrea will talk about this. So I don't want to, so then I wrote down the final estimate, but I mean, if you don't have written down the approximation estimate, it doesn't mean anything to you, but the point is that you can write it, or you can actually find the convergence rates. So what about Maxwell? I consider frequency domain time harmonic Maxwell, and I assume with impedance boundary conditions, and I assume to have constant coefficients. Again, my assumption of constant coefficients is because I have to apply a duality argument and I need to have high regularity of the dual problem. So that's why I cannot get rid of this assumption in my analysis. So you can write the method with variable coefficients, that's not a problem. But since I'm concentrating on the analysis, I'm setting all the assumptions which are needed in our analysis. So the derivation and the formulation of Trefts DGFEM, you do basically the same I did for Helmholtz, and you find and you write down your Trefts DG method for Maxwell. So I'm not deriving that. Then this is a remark that if you take Trefts basis functions for Maxwell, so automatically you have that within each element you have divergence-free property, because so this is my equation. Trefts means that my discrete function satisfies that this one is 0. If you take the divergence of the equation, so here you have divergence of the curl, which is 0. So if this one is constant, here you have simply divergence of WVP is 0. So you have a local divergence-free property. So if you want to use plane waves, for instance, you have to use divergence-free plane waves. So you cannot take any plane wave you want, but you have to assume to have divergence-free property. This is a little bit technical, but is obvious. So this is a reminder, the scheme of the analysis for Helmholtz. Step 1, mesh norm well posedness. Step 2, elliptic irregularity, L2 norm estimates. Step 3, best approximation estimates convergence rate. Now we would like to do the same for Maxwell. So step 1, it's fine. Step 1, you set this triple norm as, now we know the trick, as the imaginary part of AHWW. And again, so you write everything up, And you see that this one actually is a norm in the Trefts space, Trefts for Maxwell, of course. Then again, this is technical, and then you have basically coercivity by definition, and you can prove very easily continuity. So then you have well-posedness of your discrete problem and the quasi-optimal error estimates in this mesh-skeleton norm. So basically, step 1 is fine, exactly like for Maxwell, for Helmholtz, sorry. There is a little problem that people working on Maxwell equations are very much concerned about. The global divergence-free property of your discrete solution. So if you do Trefts DG, you cannot expect a global divergence-free property for your discrete solution. Why? Because this norm, if you write down this norm, which is the imaginary part of this, you see that it controls only the tangential jumps and not the normal jumps. So even if you have that your solution is locally divergence-free, is divergence-free within each element, but then cannot be globally divergence-free because you don't have control on the jump of the normal component. Because to have globally divergence-free, you need local divergence-free plus zero jumps in the normal component. And here, this is something you don't have. So either you resort to a modified formulation, otherwise you cannot hope to have a global divergence-free property of your solution. So this is the first warning that the analysis gives you. Now, we would like to do step 2. So let's see if we can bound the L2 norm by the FH norm like we did for Helmholtz. So we know the trick. We write the adjoint problem with the general right-hand side. So this one is the adjoint problem. But then, if you look at this, even if W is a Trefts, then you cannot, so W is a Trefts, but then you cannot perform duality argument because you have elliptic regularity of Maxwell. This is the theory of Maxwell. You have elliptic regularity of Maxwell only if the right-hand side is divergence-free. So the elliptic regularity theory for Maxwell works only if the right-hand side is divergence-free. But now I want to choose W as a Trefts function, but Trefts are not divergence-free. So the standard duality argument, well, not the standard, but not even the Helmholtz duality argument work. So we decide to do the usual trick that is common in the Maxwell community, to do Helmholtz decomposition. So I split my Trefts functions, which is not globally divergence-free, into divergence-free function plus the gradient of an H10 function. And then I estimate this and this separately. Then this decomposition is orthogonal in L2. So if I bound the norm of this and the norm of this, of course, I can bound the norm of W, because I would like to have something like this. So for W0, for the divergence-free component, I write a problem with here W0, duality argument, and it works. So basically you write the dual problem now with the W0, so now you have divergence-free property. And then the problem was that everybody knows elliptic regularity results with either with the Dirichlet boundary conditions or with Neumann boundary condition, but not with impedance boundary conditions. So what we had to do was to establish new stability and elliptic regularity results. So the main thing is that you can see that you have a stability results with this impedance boundary condition of this type, that the H-curve norm of the solution is bounded by the L2 norm of the right-hand side with a constant, and this is the important thing, which is independent of omega. Because in principle we knew that here we had a constant, but it was not clear whether this constant should depend or not on omega, and now we could establish that this constant is actually independent of omega. And then this is an elliptic, very weak elliptic regularity result, not in H1 norm, but in H1 plus S norm, with S is between 0 and 1/2. So here you never have 1. You have a little bit less, more than 1/2, but less than 1. And this is basically the corresponding stability and elliptic regularity that for Helmholtz everything, for Helmholtz everything was already known. Here we had to develop. So if you use this, you end up with an estimate of the L2 norm of this by constant something times the skeleton norm of W. Now, gradient of P. So here everything is all right. You bound the L2 norm with this one. Unfortunately, you cannot bound the L2 norm of the gradient of P, the second component of the Helmholtz decomposition. So what we had to do was to bound this in a weaker norm, which is basically the dual norm of the H-div norm. The H-div norm is the graph norm of the divergence, and here then you have a weaker norm than L2 norm, which for divergence-free functions it coincides with the L2 norm. But if you have any H10 function, this is not this is not divergence-free, and so you have this weaker norm. And we could obtain this bounding, this weaker norm of the gradient of P by the skeleton norm of W. This is the weight that you have in front of, by using the Laplace elliptic regularity, so the elliptic regularity for the Laplace equation, and again another Helmholtz decomposition and the L2 orthogonality of the Helmholtz decomposition. So since we already had stability, quasi-optimal error estimates in this norm, then you end up with error estimates in this norm, which is a little bit weaker than the L2 norm, but which coincides with the L2 norm for exactly divergence-free functions. So this is basically what we did for Maxwell. So step 1 is like for Helmholtz. Step 2, we had to establish new elliptic regularity and stability estimates for the inhomogeneous adjoint problem. For Helmholtz was easy because these estimates were already available. And then instead of L2 norm like for Helmholtz, we could establish error estimates in a volume norm which is a little bit weaker than the L2 norm. We used again a modified duality argument, but in this case this is a modified duality argument, because in order to apply our duality argument, you also had to use a Helmholtz decomposition. And the reason why, I repeat, the reason why here we cannot have the L2 norm is because when you write the Helmholtz decomposition, the gradient of P, which is one of the two terms in the Helmholtz decomposition, is not smooth enough. So the regularity of the gradient term is too low to be able to estimate, to bound the L2 norm. Again, I leave Andrea for the technical and difficult part of the convergence estimates, and I come to conclusions. So I presented the derivation of Treff's DG for Helmholtz, and for Maxwell I just say that you do the same, but is really almost the same. And I presented abstract P convergence analysis. So it's actually HP convergence analysis, but for H, since you can do better, I didn't want to enter. I don't want to claim that this analysis is what you should do if you want to perform an H analysis, because you can actually do better. And for the convergence rates, so since I didn't enter into this, I just want to summarize what we have and what we don't have. So for the two-dimensional case, we have H version analysis and the P version analysis with convergence rates which are fully explicit in H, in P, and in omega in the frequency, whereas in 3D we have a fully explicit H version error estimates, whereas for the P version we have error estimates where the constant depends on a parameter which depends on the element shape in an unknown way, and Andrea will be more specific on this. So basically everything is explicit in omega, h, and p, but here there is a parameter that even if your elements are convex as usual, you can take triangles, squares, we don't know what this parameter is. The main drawback of this kind of methods is the ill conditioning also for moderately high p, and this is a list of open issues. So to complete the analysis for Maxwell, to fill this gap, another point is to explicit convergence in broken H1 norm. We have an error estimates on some approximation of the gradient, but not really of the gradient. And then to see if we can modify our analysis in order to deal with the known quasi-uniform meshes, with known constant coefficients, and then what is also under examination is, in the case of plane waves, to see how to choose directions adaptively. Because so one of the freedoms that one of the possibilities that the use of plane waves gives you is that you are not forced to choose uniformly spaced directions. So if you have information of your problem, so you can use some ray trace in order some technique to find some directions you want to have in your space. And this is something else you can exploit if you use, instead of general Trefz spaces, plane wave Trefz spaces. Okay, so this is all I wanted to say, and I wish to thank you for your attention.
Thank you very much. It was a lovely talk. And we have time for a number of questions. So please go ahead.
Yeah, I'm sure that you have run some numerical experiments with your method. 2D case, 3D case?
2D case.
2D case.
2D.
So what's the maximum wave number did you use?
Not very high, because the problem is with ill-conditioning.
Right.
So if you don't have a good preconditioning, you can really not run. I mean, it's not a problem of the method, but it's a numerical problem. The problem is ill-conditioning, because so the point is that you should find. So the point is that with this kind of space of bases, so if you increase omega or you decrease h, what you have is that your functions are becoming linearly dependent. So if you really want to use to run experiments with high omega, you really have to modify your basis functions or to precondition. So you can put a problem in a different way.
How wave number did you try?
How I
Up to.
up to with order 10, not order 100, right? Order 10, I would say. Yes, because the problem is with the e-condition. At some point, so if you don't do anything, nothing clever, it kills you.
Definitely. You have
Yes.
Simon?
Yeah, can I ask about the Maxwell regularity results with
Yes.
the frequency explicit? This is derived with, is it some sort of relic?
Well,
Type argument?
somehow. So basically, so we tried to repeat the same reasoning either by Marcus Melenk for Helmholtz or by Etmanuk again for Helmholtz 3D, which is a kind of, so you choose in a clever way the test function and you proceed. We use an intermediate result by Doge, Costa, Belenikez, and so everything is not written in a complete way, but we have this proof basically.
And this is, what class of domains is this for?
Yeah, that's the problem. So let's say you start with a smooth domain, so you apply Grisvar technique and you go to Lipschitz domain. So what we know now is that convex is fine, convex Lipschitz, and I'm not sure if we can finish to work all the details to have a domain with a hole, which is what you would like to have, I guess.
Okay, let's thank you, Ilaria, again.
Thank you.
Thank you very much.